Welcome everyone to this ROS Industrial Conference 2020 session on full stack solutions for robotic software development. My name is Dr. Björn Karl from Fraunhofer IPA in Stuttgart, Germany, and I will be your host for the next 1 hour 15 roughly. Before we start the presentations, a few words about today's conference format, also most of you probably already know. You will have 3 presentations, each about 20 minutes, including questions and answers. Followed by a joint discussion round of about 15 to 20 minutes. All of you following us at the conference website should have a live discussion box at the right of this session's page. Please post any questions or comments you may have for our speakers under the questions tab in that box. I will read the posted questions to our speakers, either directly after the presentation or at the final discussion round. With that out of the way, I have the pleasure to present our first speaker, Pablo Puelles, a former researcher from Fraunhofer IPA Stuttgart and currently co-founder and head of technology at the DRAG&BOT, a young startup company. He will present their cloud robotics for industrial automation solution from digital twin to production. Please, Mr. Gillet, the floor is yours.
Hello everybody, I hope you can hear me. So thank you for the introduction and for the opportunity to be here. So this year we want to present the progress we did during the last time, and we will focus the presentation in cloud robotics, so how you commence from the digital and you end up in production. A little bit the story about us. So our company is relatively young. So I started 2-3 years ago officially, but the idea is very old. So we started at DRAG&BOT. So the idea behind Fraunhofer IPA, so where we were researchers. And so after starting with the prototype and the business plan, so we got positive feedback from the market, which led us to get investment first from the government, German government, which allows us to complete the different pilot projects. And after that, so we got venture capital to finance our own office. And so currently we are more than 10 employees. And yeah, so we are doing some progress in the last time. Good. So you see now the team. I want to start with the reason why DRAG&BOT exists is because we identified different 3 main trends in the market, which are so the first one is in robotics. So you have a very huge background of different components, different interfaces, hardware, programming, and this leads to the challenge. So how you put everything in common to got the automation. So how you deal with the limitations and so the different equipment. So therefore, so DRAG&BOT tries to offer operating system which ensures cross-compatibility and also unified operations, so which is the same for independent of the component. The second trend is that product life cycles are getting shorter and shorter. This means we have an increase in the frequency we need to change production. And therefore, so there is the challenge, so how you fit everything in the market to make the cost profitable, because every change, so you need more money to adapt your production, your machine, your configuration, and this leads to costs. Therefore, DRAG&BOT offers this easy way to reconfigure all the components in a very short time. So if you change, for example, gripper, so you don't need to deal with technical difficulties, but so you just configure it in our interface and it's working. And the third trend is that companies are willing to automate more and more every day, so which leads to the complexity that they don't know. So they don't have this know-how and this technology, so they don't know how to start. So imagine a small company which have never automated process and they want to automate something. So typical way is you go to the system integrator and you get a big so an offer with a big amount of money, which is sometimes very expensive. Therefore, so we try to make it simple and very easy for this automation, so reducing the cost. If we see in detail the features we are offering, so these are the main points which includes our software. So the first one is you don't need to program with code. So it's graphically everything. So there are two ways of programming. One is the with phantom blocks, and another one is with different guides and wizards, which is completely graphical. The second is that everything is customizable and extendable, so which means you can adapt to your necessities, and also you can include new panels, new information, new wizards, so new ways of displaying, so how to use hardware components, and also integrate different third parties components. Um, Hardware agnostic, so it's to make the integration so independent of the hardware, so which means if you replace your robot with another robot, the same program is going to work, and also if you replace your PLC with another one, so it's working in the same way. And this everything leads to the plug and play interface, which is our vision, our philosophy. You can connect everything. It's just like in a computer when you connect a mouse or a printer, and it's just working out of the box. If we see a little bit in detail the scope, DRAG&BOT covers all the necessities of the factory floor, starting from the robots, for example. So there is a big, I think we now support more or less 10 different robot manufacturers, and cameras or vision systems, PLCs, different grippers or sensors, feeding system, and we offer the opportunity, so the possibility to integrate any kind of hardware very easily through our API and SDKs. So this is why this third-party software is very important for us. From another point of view, DRAG&BOT covers this scope through 3 different steps. The first one is the planning, which is it's the simulation. So you can create your own program, define your own cell there, so your scenario, and then you can test, for example, the reachability, the cycle time, and also the return of investment. You can also load your own CAD models so in your environment and do simulation with them, so you can grip them, so you can use them. And also, of course, create your program, the logic, and run it, everything in the cloud or also online, so or locally, I mean. The second step is how you integrate in the reality, so this build and setup. In this case, so you just connect the components, and maybe you need to parameterize some small things like the IP address or some parameters, and then everything is working. Everything you already simulated before. We offer different ways of teaching. So, for example, a teach pendant from our side, or the new motion mate. We will also is a way to teach new positions and new paths. And so you can control with even from a gamepad to a real robotic teach pendant. And the third step is the operator, so where you run everything. So DRAG&BOT is not the tool, it's not only a tool for planning and integrating, it's also for running. So this allows workers to have a custom human machine interface where they can control the process, modify parameters, start stop program, and see the key performance indicators. Moving to the next step, so to the next slide, in this case, we see a little bit more information about the planning. So you can design everything in the scenario designer, where you load the CAD models, and then you can configure the properties. This is in combination with the builder, where you after create your own program. So I don't want to stop too much here at this point, because I will do a live demo at the end of the presentation, and then we'll see everything in detail. So in the second step, we display here one example. So it's the motion mate. So In this case, so it's the new way how you can teach the applications. So you just need to configure your hardware and place the two sensors around the workspace and then mount the calibration tool on the robot flange. You run a small calibration program, and then so you have the tracker calibrated to your robot. I also want to thank because this is so in the past was there are some research were done in this aspect, and so I think is yeah, it's quite interesting idea. So this is why we decided to go for this. So in the next step, so you configure the software, yes, in DRAG&BOT as standard components. So you just need to click in a dialog, and then everything is installed. And the third, so is the teaching itself, where you just take with your hand the tracker, and then you teach the positions. Moving to further, here we see an example of the human-machine interface. We call it operator's cockpit, where you see the current execution of the program, and you can interact with different dialogues, deactivate the panel. So for example, if you are interested in displaying the IOs or a camera, so you can move also the position of the panel and display also different key performance indicators. For example, how much products you produce, or the quality of the part if you are doing quality inspection. This is very configurable, so you can always integrate third-party GUIs. So we provide a small SDK for that, and also there is a generic way to display any kind of website through a URL displaying so system. In this case, so we use quite a standard for displaying the smart cameras, so the web interface from the smart cameras, and then you don't need to deal with complex integration. So you just display the IP address, and then you can also access to the camera. As this is a ROS Industrial, as is a technical meeting, so I wanted to show a little bit about our cloud architecture and so the process, how it's working. So in the first step, you come to I think, I don't know if you see my mouse. So here we start. So in dragbot.com, you can come there and register for free. You get an account, and a simulation code is generated. And after that, so you can use your account. So in DRAG&BOT Studio, which is the application, you can log in, and with your code is generated a new runtime instance. In this case, the runtime instance is a complete simulation running ROS in the cloud, so in a Docker container and in a pool of different machines. Normally it lies for 10 hours, but you can also have a persistent on demand. So if you are interested in having a runtime, which is always active, we have a quite of clients which are interested in this aspect, then so it's the possibility. We run the full simulation there, which includes the inverse kinematics and the path planning, and also some simulated hardware and software components. And this is controlled by a tool we call Simulation Dispatcher, which is managing the creation and destroy of the instances. Given a new code, so generates the instance. In contrast, I wanted to show the local system where everything is installed there. So this includes the studio and also the simulation with the runtime, and the connection to so the drivers to connect to the real robot. This is the preferred way from industry, but they are so in production. I mean, they always want to have everything installed locally and control from there. But they are also open. So in the first step, to use the cloud, so to prepare the programs and prepare the simulations and do these changes. Going to a real industrial application we did in the past. In this case, we are showing industrial, so it's application based on the machinery. So it's a process where the robot picks a part from a tray, puts in the machine. The machine does some process. In this case, it's polishing, and then takes back from the machine and puts in the tray. You can see the video also in the ROS contents we have uploaded it. And the advantage for the customers is that they can reteach the application without managing with robot programming. So they just configure the size of the part, the process itself, and then is everything automatically adapted to the new production. Well, going to the live demo. So as I say, so in the first step, you go to drag&bot.com and then you can register. So I will show you live how you can connect. So wait 1 second, I change the screen. I think. So I share again my screen. So I hope this is the correct one. Yes. So as you see now it's loading. So you go to the website and then you can log in here. So 1 second, I will log with my data. So I deactivate. And once you log, so you come in the main view. So in this case, you see our system. So the first step you see is this welcome screen where you see the different programs you executed in the past and that the robot system, so the hardware which is configured. In this case, so as I'm not connected with any robot system, I need to create a new one. Therefore, so there is the simulation code, which in this case is ROS Industrial 20. And then automatically the instance is created in the cloud. So now there is a real simulated robot which is running everything in the internet. So you can see now if I change to the scenario designer, I see the current scenario which is here configured. So it's loading the CAD model. So you see here the machine, and here you see the conveyor belt with the table. Also, if you want, so you can change the road, for example. I can change here between different kind, so different wide brands of robots. In this case, so I can change to the KUKA, and you will see. Now it's changing the robot. And now the new robot will be displayed. So you see now it's quite bigger than before. You can move it. So in the simulation, so I think this is my skin is a little bit small. So you can move it here in so for example to program. Also there is this different kind of tabs where so you can close, open the gripper, and also see simulated IOs. And there is a data store, so it's a registry for having persistent data. Going to the builder, we can create a new application. For example, move Cartesians. Yes, I can teach the position. So I teach the position with the current, so the properties, so changing to lean, PTP, this kind of thing. So I just move the robot a little bit down, example, and I can run the demo. So now the robot is already moving. So this is everything is running fast. And because I just have a couple of minutes, so I wanted to show that you can add new components, so which are displayed in the list. So depending also if you are working in the cloud or locally, so you have different kind of simulated components. And we prepare a small, nice thing for this going back to the scenario manager, so you can import your own scenario. So everything you did, you can import it again. So select file, I load the scenario, which is going to update the scenario now with a little bit more Christmas fancy tool. And also we prepare, I think I need to, you can change the tool you are using. In this case is using this Smalls vacuum gripper. Everything you can export and import it again. And once so you have the scenario, so if you come to the program, so you see here is it's a real program, so you can run it. In this case. And now, so the robot is going to put, so to do a palletizing application, so to pick the balls from the pallet and put on the Christmas tree. So you see is the robot is doing it. And if you take this program, this configuration, so with the local runtime version of DRAG&BOT, so you can use directly with your own robot. And I think I'm a little bit out of time, so please correct me if I have more time or not. But in this case, so we are already finished. So thank you everybody for your attention, and any questions, so I will be happy to answer.
Okay, thank you for your interesting presentation and also for the quite impressive demonstration. We are somewhat short on time. For that reason, I would like to move the questions to the final discussion round and instead continue with our next speaker. The next speaker is Mr. Herb Gutter. He is a senior staff software engineer at LG Electronics in America, in the Research and Development Center there, and the lead maintainer of MetaROS, the open embedded layer for ROS and ROS-II. He also works on the LG SVL simulator, a specialized simulator for large mobile robotics with 4 wheels, better known as autonomous vehicles. This talk will cover how open embedded, MetaROS, and WebROS can be used to build more capable industrial robot products. Please, Mr. Gutter, it's your turn.
Hello, everyone. Again, my name is Herb Gutter. I'm going to talk about building lower cost robots with advanced capabilities using WebOS, MetaROS, and WebOS. So here's an overview of what I'm going to discuss today. I will go through the introduction and motivation behind using low-cost embedded hardware and embedded Linux for industrial robots. Then I'll discuss what development with ROS and Open Embedded, which is the flavor of embedded Linux, looks like, and some of the work we've done to enable this. And I'll talk about how LG's open source operating system, WebOS, can enhance robotics product development even more. And I'll finish with a demo video. It's from ROSCON 2019, since the pandemic has prevented us from creating anything new this year.
We can't see your presentation, we see your video.
Oh, I'm sorry. So, that's what I didn't, I'm sorry, okay. Well, you haven't missed anything.
Perfect.
Okay. So the challenge that ROS Industrial was set up to take on was the observation that industrial robots are not being designed for new tasks. And why was that? A lot of great work was being done by the robotics R&D community, but it was not making its way into new robot products. But the goal of transitioning robotics R&D into products can't be met without actually building the product. And from a product point of view, there are lots of expectations that need to be met. You may need slightly different variants of what your company sells while maintaining reproducibility of your deployment of all of these. At the same time, you need to keep up to date throughout the product lifecycle with software and security. Plus, you need to be competitive. You want to offer advanced capabilities and user experiences, and of course, all of this at the lowest possible cost. So how can you create these products while keeping production and development costs low? One possible path is to reduce the hardware costs and simplify the software development. And you can do this by using mass market embedded hardware and using embedded Linux development. So first, let's take a look at some of the characteristics of mass market embedded hardware products that are already being deployed and scaled globally. These include things like smartwatches, smart TV, mobile phones, routers, etc. These products have embedded hardware built from low-cost system on chips. They are customized for dedicated functionality and have a low memory footprint, low power consumption, and while still having real-time performance. Every use case has these things to be as fast as possible, and for devices with displays, as rich a user experience as possible. Embedded Linux of one sort or another enables most of the mass market devices that are out there. So an industrial robot could take advantage of this low cost but highly performant mass market embedded hardware by having it replace the usual PC and robot controller. And also being able to, if you again want the robots to evolve to for industrial robots to evolve to perform new tasks, then you need, perhaps you want ones that have touch panels built in and aren't necessarily just an arm that's fixed. But anyway, one challenge though, at least for traditional software, Linux software development, embedded software development, is its high cost. With traditional embedded development, there can be many challenges in this process. You need to support multiple hardware variants. There's cross-development and support of different architectures. Significant customizations need to be made for every product line or version. And of course, many optimizations need to be done to fit into the form factor you've chosen. So as you can see, there are challenges associated with scaling robots that are common to embedded devices. Our solution for commercialized industrial products at scale is to use embedded hardware, open embedded, a base embedded Linux that simplifies the challenges with software development, add ROS to bring in the robotics capabilities, and then put in WebOS, which is LG's open source embedded Linux deployed on millions of devices, which may bridge some of the gaps to actually finishing a product. Let's see the parts of this solution in a little more detail. Next, I'll discuss the work we've done to enable robotics development on open embedded. Let's start by giving you a brief introduction to open embedded to hopefully give a feel as to why LG uses it to simplify its developed embedded devices. You can find more detail at the link shown at the bottom of the page. Open embedded is the build system for the Linux Foundation's Yocto project. It allows cross-compilation for many different CPU architectures, including RISC-V, by the way, and a wide variety of chipsets and boards are supported. It provides a open embedded Linux, which is a collection of component versions that work together and provide a baseline embedded Linux. It's customizable in that you can select exactly which packages are included in the image for the device, configure them to only include the features that are needed, and compile them for the exact CPU architecture used by your product. It takes as input recipes and configuration. A recipe specifies from where you get the source for a component, how to build it, and how to package it. It's sort of the same thing that ROS's package.xml specifies. Everything is built from source, even the tool chains. It creates builds that are reproducible. The versions of all the packages are pinned in the recipes, and therefore the recipe must be changed in order to build a new version of the component. It's organized into independent layers. They are given a meta prefix. There are ones for boards, for example, Meta Raspberry Pi, ones for functionality, for example, meta networking. So why not a meta ROS? Well, actually there was one. It had been maintained by Lucas Balwan of BMW Car IT, but when we looked at it about 18 months ago, it had lain fallow and it hadn't been updated since ROS-I Indigo and didn't support ROS-II at all. And why was this? Well, ROS contains thousands of components with dozens changing every couple of weeks, and manually updating the versions and the recipes was too daunting a task. So what we did about 18 months ago was to decide to generate them. There was an existing tool from the ROS community called Superfloor, and it had been used to generate recipes or releases for other platform OSs. And what we've done is enhance it to generate open embedded recipes. Superfloor takes as input the ROS distribution cache and platform package mapping file and generates open embedded recipes for the selected ROS distro. In order to generate recipes for the exact versions of packages that appear on the ROS distro release announcements, we generate our own cache.yaml from the commit of the distribution YAML from which the ROS distro release was made using the ROS distro build cache tool. This scheme allows us, has been very flexible and productive, and it allows us to support all 6 of the current ROS-I and ROS-II distros across all 3 of the current open embedded release series. We made it very simple to build a ROS image with MetaROS. All you do is you clone the repo, you set up the open embedded layers needed based on the ROS distro and the open embedded release series you decided to use. As I've showed here, we've chosen the ROS-I melodic and the long-term support release of open embedded named Dunfell. The next thing you do is you set up the build environment. You edit configuration settings for the build that's found in the local.com file. And then you just run bitbake to build the image, passing in the machine you wish to build the image for. It's also easy to add a new ROS package to your image or to modify an existing one. Just clone this repo, run a script to generate its open embedded recipe from its package.xml, add the package to your image by editing the local.conf, and run bitbake again to create the image. For more detailed instructions, please take a look at the links at the bottom of the page. So not only does Open Embedded simplify the building of software for embedded devices, it also simplifies their deployment. For example, the current scheme for deploying from the the Raspberry Pi based Turtlebot 3 is shown on the left. Now, granted, this is not an industrial robot, but I'm guessing they use a similar sort of scheme. So one has to go through a long number of steps. One installs Ubuntu, ROS, and the Turtlebot 3s on a remote PC. Then one installs Ubuntu and ROS on the Raspberry Pi. Then they compile the Turtlebot 3 package on the Raspberry Pi. Then one has to SSH into the Turtlebot 3 to configure its instance information, configure it to talk to the remote PC. You have to launch ROS Core and the Turtlebot ROS applications on the remote PC. And finally, after launching the Turtlebot 3 ROS nodes on the Raspberry Pi, the Turtlebot 3 is operational. Now compare this with if it's Open Embedded based, you've built an image with the specialized Open Embedded and ROS components on a build PC, which is much more powerful than a Raspberry Pi, so it doesn't take hours. You load it, you flash the image on the Turtlebot 3. You can load device instance configuration, for instance, the host name or the Wi-Fi SSID, and the Turtlebot ROS nodes to start upon by booting from a flash drive, and then the Turtlebot 3 is operational. And you can see how much quicker and easier it is to configure using this approach. By building everything from source, the security of your product can be enhanced. if you configure components to have only the features that are used compiled into them, there's a smaller attack surface. If an exploit is found in some feature that your product isn't using, it won't be effective. A more radical idea I've had, but I've never tried, would be that since you're building everything from source, even the tool chains and the kernel, you can make things like the kernel system call indices or the executable file format or the layout of the processes and memories be non-standard, which means that attacks that expect it to be in the standard at the standard formats and locations and indices will fail. Of course, this won't work if your hardware vendor doesn't supply source for all of the device drivers, which unfortunately a number of them don't. Another thing that Open Embedded helps with is that one of the issues with building commercial products that use open source is being able to publish the licenses of the components they use and making sure that none of them have licenses that exact an undesirable burden, for instance, GPL v3. Open Embedded simplifies both of these by collecting all of the licenses of the packages included in the image as a build artifact. And it can also be configured to warrant, say, if a GPL v3 component is being used. I'm showing here last week's GitHub traffic report for MetaROS. There's several hundred unique clones and views, so it appears to be fairly well received. I've talked about how using Open Embedded simplifies building and deploying embedded devices, but it only provides a baseline embedded Linux. I will now explain how adding another layer, the one for WebOS, can provide a collection of rich product features that help make a complete product. So WebOS is LG's open source operating system, and it powers many, many LG devices. It's built upon Open Embedded, and it has a feature-rich set of collections for end products, and it has a proven built battle-hardened quality because we've been shipping millions and millions of devices. There's also a variant of WebOS called WebOS Auto that has been announced, and I believe it's been adopted by several automakers, although I don't know by whom, and if I did, I probably couldn't be allowed to tell you. But Open Embedded with ROS and WebOS, here are the advantages. It would be optimized for embedded hardware, so it has low power, low CPU usage, low memory usage. It has advanced capabilities and rich user experiences. It's called WebOS, meaning it uses a web-based application development scenario. It provides a software update pipeline, so you can update devices over what we call over the air, but from the cloud to device, and it's free. You're allowed to rebrand it and redistribute it as you like. So here's an architectural overview of WebOS. As you can see, there's a plethora of services and features available. I'm not going to go through everything, but I do want to highlight a couple besides the software update that I just mentioned. There's the LS2 message bus that allows components to talk to each other. It's exactly analogous to the ROS message bus that you're familiar with. It has sophisticated localization, and internationalization support. There's built-in support for Google Assistant, on top of which is built an AI voice service and text-to-speech service. There's a context intent manager and workflow designer based on Node-RED. This allows you to add workflows and AI logic to your web app without having to modify its source code. Also, what's not shown is support for virtualization and containers. We've been working on another variant of WebOS, we're calling WebOS Robotics, that would be optimized for robot products. We imagine that it would provide a common base platform upon which multiple robot variants could be built. Particular to it would be, of course, Meta ROS, and then a bridge between the WebOS LS2 message bus and the ROS message bus. So here's an example of how a common base platform might work. This happens to be for variants of robots that can move, but you can imagine the same idea might apply to industrial robots. You can see it supports multiple reference hardwares. There's a common set of WebOS features that are used and a common set of ROS features that are used. And then each particular variant of robot has its own ROS-specific and WebOS-specific layers or features. And in conclusion, I hope you'll be able to agree that this combination of open embedded, Meta ROS, and WebOS is a path to building lower cost industrial robots with advanced capabilities that will allow industrial robots to migrate and evolve into performing other tasks. So this is the demo I promised. Again, it's from last year's ROSCOM. So if you, again, just give it a go here. Oh, nope. Oh, let's see. Whoops, I'm sorry. I think I got to stop that. Sorry.
everyone, and welcome.
I'm sorry, people. There we go. Anyway, and I don't know, I think I'm out of time, so I guess we'll have to ask to have any questions at the general session.
Okay, thanks for the presentation and also for the nice video. Indeed, we will need to have the questions collected in the roundtable discussion. So we will move on to our final speaker for this session, which is Mr. Matthew Hansen from Amazon AWS Robotics. Matt Hansen is a principal solution architect for AWS Robotics. He has been working with ROS since 2015 and previously led the ROS radio sense camera and navigation 2 projects. He has been a representative to ROS Industrial for nearly 2 years and has been with AWS Robotics focused on RoboMaker since February of this year. He will present his work on accelerating robot development with AWS RoboMaker. Please, Mr. Hansen, it's your turn.
Hello, everyone. Thank you for the introduction, Bjorn. My name is Matt Hansen. I am a principal solutions architect with AWS Robotics, and I'm happy to be back at ROS Industrial presenting. I've presented here in a previous role. I have the mug to prove it. And so today I'm going to talk to you about accelerating robot development with AWS RoboMaker. One second, though. Let me get my note screen up here so I can see that. So the agenda for today's talk is, first I'm going to introduce you to AWS RoboMaker and cloud-based simulation in general, and then I'm going to go over a few different simulation use cases, which I think you'll find interesting. I'm going to introduce you to a tool we have called WorldForge, which is part of RoboMaker, and our batch API. Then I'll talk to you about the ROS open source contributions and resources available to you before we do questions if there's time at the end. So as all of you on this call probably know, demand and usage of robots is on the rise. Logistics, healthcare, and consumer are 3 of the fastest growing segments of the robotics industry. 2023, autonomous robots will emerge as the standard for logistic and fulfillment processes. Global medical robot expenditures are expected to increase by 20% by the year 2025. And household robots are expected to grow from 3.3 billion in 2019 to 9.1 billion in 2024, nearly 3x growth in just 5 years. To meet that need, robotics companies are developing increasingly advanced robotics applications. But as you probably also know, being on this call, building robots is hard. You have to develop, test, and deploy your robots. And development requires multi-domain expertise. You have to know hardware, you have to know software, and you have to integrate and test and iterate in order to get it right. That can be very time consuming. There's limited robot hardware, especially in the early design and prototyping phases. And there's often restricted access to physical environments to test your robot in. And it can be expensive to build large labs, mock warehouses, mock hospitals in order to test real world scenarios on your robot and validate your software. Simulation can help, but simulation can also be a little bit costly to get going and to scale. Finally, there's deployment. Deployment is a critical part of your software development flow in that as you make changes, you need to update your robots in the field. You need to be able to do over-the-air updates, and you need to be able to track which robots have which updates when and which robots do not and still need to be updated. So this is where simulation comes in. As I mentioned, building robots is hard, as many of you already know. Testing software on hardware can be a development bottleneck, but simulation allows you to gain confidence in your software before putting it on your hardware. Therefore, you can test your hardware and your software in parallel and decrease that bottleneck. You can also automate your software testing into your workflow to ensure that every new code change is working prior to merging. We'll talk more about that as well. So why should you do simulations in the cloud? Well, it's all about scale and quality, right? With the cloud, with simulation, you get the most out of simulations when you can run a lot of them. So you get much more robust testing when you run a lot of simulations, when you test a lot of scenarios. For example, you may want to test your robot around stairs or ramps, and different building configurations, different objects in the world, for example. And then you can also scale the number of environments. So you can scale the shapes and sizes of the worlds and the number of worlds. And finally, for reinforcement learning, you can use simulation to accelerate your training of your machine learning models. And you can do parallel simulation and use that feedback to accelerate your machine learning, reinforcement learning training. So AWS RoboMaker was designed a couple of years ago with all of these problems in mind. And RoboMaker is a service that provides enterprise-grade reliability with built-in system checks and a managed ROS and Gazebo software stack, which gives you reliable simulation and makes it easy for you to develop, test, and deploy your robot software. RoboMaker has 4 main areas of capability. There's the ROS open source tools and cloud extensions. There's simulation capability in the cloud, a development environment in the cloud, and fleet management, which uses the cloud to deploy and update software to robots in the field. Today, we're focusing primarily on ROS and simulation in the cloud using RoboMaker. Here's a high-level view of the RoboMaker architecture. Developers can use our IDE to create robot applications based on ROS. Then they can upload them to S3 and simulate them in the RoboMaker simulation. They can interact with the simulation using ROS tools such as Gazebo and RBiz. They can also connect to other cloud services such as CloudWatch for logging, Kinesis for video streaming. Finally, they can deploy their code over the air to their physical robot when testing is complete. So now I'd like to discuss some of the common uses of simulation in robotics. First, simulation enables regression testing your robot software via a CI/CD pipeline, ensuring high quality of every checked-in change prior to merging. Second is multi-robot simulation, concurrent simulations which are then bridged together, allowing for testing of things such as your collision avoidance algorithms or even cooperation between robots completing a task. Third, you can use simulations to train machine learning models more rapidly by running your simulations in parallel instead of sequentially. Let's take a closer look now at the regression testing use case. Milvus Robotics makes a UV disinfecting robot for hospitals, which is increasingly important and a rapidly growing application. Because of this growth, they needed to increase development velocity while improving quality and maintaining high safety standards. Real-world testing was challenging because they couldn't get access to real hospitals for testing, and building mock-ups was expensive and time-consuming, as I mentioned before. This made finding software defects difficult and slow. But with RoboMaker, they were able to run simulations in a virtual hospital, automate their testing, and speed up their development flow. As a result, Gokul Ertunç, the co-founder and CIO of Milvus Robotics, has said, AWS RoboMaker simulation helped us save money and time and eliminate obstacles to scaling our testing efforts. With RoboMaker, we can forget about infrastructure and focus on development and testing. We implemented a RoboMaker simulation CI and can now easily test our robots in different environments, resulting in a huge quality improvement. So here's a video of Milvus testing their UV disinfecting robot in a simulated hospital world. The robot is moving around the hospital room with 3 hospital beds, and the blue lines you see represent the laser scan it's using to sense objects around it as it disinfects autonomously. Here's a short clip of a PR2 robot, which is an open source robot many of you, I'm sure, are aware of, running in the same hospital world that Milvus uses. The point of this is to show you that this world is available open source along with the sample application that we provided. It uses the PR2, so you can run this yourself. And we're hoping that this will enable developers to get started using this hospital world in their CI/CD pipelines very quickly. If you'd like more information on this, you can see the blog here linked at the bottom of our AWS website. I'll provide more links later too. The next use case I'd like to talk to you about is multi-robot simulation in RoboMaker. We've heard from a number of customers over the last few years about how difficult it is to test orchestration and navigation of a fleet of robots. As an example, when you have multiple models or types of robots operating in the same environment, relying on physical robot testing requires significant logistics work before you can even begin to test them. Right? Testing them in the real world is difficult. So AWS RoboMaker enables you to simulate multiple robots, running multiple Gazebo instances in parallel, and then managing the interaction between them using Gazebo plugins, and then leveraging the built-in integrations with the AWS Virtual Private Cloud. RoboMaker enables you to connect concurrently running simulation jobs. So here's a closer view of the multi-robot simulation running in Gazebo, with RViz showing the map and laser scan topics on the right, and Gazebo on the left showing 2 robots, 2 different types of robots interacting and avoiding each other as they move. This is another, we have another blog article on this as well, if you'd like to look at that as well. And here's a more detailed look at the architecture for the multi-robot simulations. So it starts with our RoboMaker batch simulation API, which allows you to launch a number of simulations in parallel in the cloud. So here we're going to launch 1 to n particular simulations, for n being the number of robots we want to simulate. Every robot is assigned a namespace, and communication is bidirectional, which enables the robots to see and interact with each other. And then the entire simulation is bridged together using ROS bridge, and the entire fleet is running. Multiple simulation jobs can be launched with this batch simulation API. Next, I'd like to talk to you about the reinforcement learning, our third use case. I wanted to share this one with you, not just because it's reinforcement learning, because it involves robots on Mars, which personally I think is very cool. So earlier this year, we held the AWS JPL, Jet Propulsion Labs Open Source Rover Challenge. It's a 4-month competition where participants from around the world use deep reinforcement learning to drive digital robot models on a virtual Mars landscape. Participants created autonomous navigation models for their robot and trained them in AWS RoboMaker simulation. The virtual robot used in this competition was based on the NASA JPL open source rover, which is a build-it-yourself, scaled-down version of the 6-wheel rover that NASA uses on Mars. Running these simulations to optimize the reward function can be very time-consuming and computationally exhaustive. So running these simulations in the cloud, engineers are able to train the robot in a matter of hours versus days it would take on your own local systems. Additionally, in this competition, we discovered that many customers found this environment to be useful, not just for this Mars rover, but for outdoor tasks such as solar panel assembly or navigating cultural robots. So this same approach applies in real world scenarios. Just to go a little deeper into this process, the training task is for the rover to navigate to a goal location. In the simulation, the robot is going to attempt many different actions and receive rewards based on the success or failure of those actions. As the robot learns over time, it will learn to move farther and farther. Eventually, it will find a goal to the a path to the goal location. And then as it continues to iterate, the reward function will help it to find the shortest path to the goal while avoiding the obstacles. In this case, the competition was, to find the optimal path, but there was also some penalties for obviously crashing into objects, or also for how much it had to, how much Z change there was. So it wasn't just straightforward roll right over objects. That would cause a penalty. Next, I'd like to introduce you to a new feature in RoboMaker this year called WorldForge. So generating a variety of environments for testing your robot can be time consuming. We learned this from talking to multiple customers. And AWS WorldForge helps to solve this challenge. WorldForge is a new RoboMaker capability that automatically generates one or more indoor simulation worlds within minutes. WorldForge provides out-of-the-box templates for room layout and floor plans that you can use to generate a simulation world in minutes. It's very cost-effective, only costing $1.50 to generate a world versus thousands of dollars to create one manually. You can use the RoboMaker console or command line interface to generate hundreds of worlds with different layouts and furniture types. Best of all is that WorldForge easily integrates with RoboMaker simulation for testing your training workflows. And I'll show you an example of this. Here's an example of 10 simulation worlds generated in minutes with different layouts and furniture from a one-bedroom WorldForge template. In the template, you can specify the number of rooms, the type of room, the number of connections between rooms, and the density of the furniture. WorldForge will then generate the specified number of worlds based on the template parameters and populate them with the correct furniture, such as beds and dressers in the bedroom and sofa and chairs in the living room. You can then preview these worlds, store them in S3, or download them to your local system. If you store them in S3, then you can easily use them through the RoboMaker batch CLI to easily run them in simulation jobs in parallel. It's very nice. And here's a use case for using that. So here's an example of using WorldForge for testing. You can see the gazebo simulation on the left with ARVIS showing the map as it is being generated on the right. This is running a SLAM algorithm. So when testing SLAM algorithms, having a variety of maps of different shapes and sizes is good for testing things like loop closure. With WorldForge, you can easily create a large number of worlds, and using the RoboMaker batch API, launch multiple simulations in parallel running SLAM. Then you can compare the resulting maps versus the ground truth to ensure correctness. As mentioned before, this can then be automated into a CI/CD flow to prevent regressions in your SLAM algorithms. Finally, I'd like to talk to you about the AWS ROS open source contributions and resources. One of the many benefits of ROS, as I'm sure most of you know, is that it's easily extensible. AWS RoboMaker has created ROS packages that can be used on a robot or in simulation to access other related AWS services, such as Amazon Lex for speech recognition, Poly for speech generation, because you want your robots to talk too, right? Recognition for image recognition, and of course, Kinesis and CloudWatch, I've already mentioned. However, AWS contributions to ROS go well beyond adding AWS cloud support. Over the last several years, AWS Robotics has made many contributions at all layers of the stack and multiple tools. Some of our most recent contributions to ROS2 to ROS2 Foxy include quality improvements in the client layer, adding a rolling distribution, improvements to ROS Launch and ROS Bag 2, quality of service improvements, and many, many more. We're also a highly active member of the ROS2 Technical Steering Committee, and we are dedicated to making ROS2 a truly production-grade framework for the long term. Wrapping up, I'd like to, I'll give you the RoboMaker team. We've created many resources available to you, open source assets in our GitHub repository. This includes the cloud extensions, which I already mentioned, that you can use in your application. We've also provided multiple 3D worlds for Gazebo that you can use to accelerate your simulation development. Hospital and small warehouse worlds that you've already seen are two of those worlds. We've also provided open source sample applications to help you get started testing your robots in many of the use cases we have discussed today, such as the PR2 in the hospital world. And you may be wondering at this point, where do I find all these useful tools and assets? So here are the links that you can use to dive deeper into RoboMaker and our open source resources. Thank you very much. And now I can take questions.
Okay, thank you, Mr. Ansen, for this interesting presentation. Actually, there's actually a question from the audience also. So we go basically in the reverse order for the presentations, and then we start the roundtable discussion. And I would like to ask for short answers so everyone has a chance. The first question is to our last presenter in the hospital sim case for CI regression testing. So what specific metrics are actually tracked there?
Well, that's up to you. So, I mean, each test case is going to be testing something different, right? So you may be, like, your simplest test case may be just testing that your robot is navigating from point A to point B across some distance, and it's reaching a goal within some, some specified area. But you can also test other things, such as can your robot navigate through doorways? Can it navigate around unmapped obstacles, things like that?
Okay, thanks. That was another technical question actually for the DRAG&BOT presentation. So Pablo, the question was, is the UI based on VS Code or what have you been used? You are muted.
Muted, yeah, thank you. No, it's everything web-based, so it's currently Angular with some standard web technologies. Because I didn't display the browser, but everything is running in any browser, so we recommend Chrome or Chromium, but so everything is running in the cloud. So yeah. Normal web page.
Okay, good. So with these two questions from the audience answered, I would like to start the roundtable discussion. So everyone has its camera on, that's nice. I will just start with the question to all speakers. I mean, we have seen a few cloud-based services now. I'm wondering is, so do you have customer feedback regarding using cloud-based systems versus on-premise solutions, or even just on a desktop PC something? I would ask first Mr. Hansen and then take the round. You are muted.
All right, I just realized I had muted while you're talking. So you're asking me first. So the question, as I understood it, was, how are customers responding to use, cloud versus working on their local system, right?
Yes.
Well, yeah, as I mentioned, I think, in our use cases that I showed today of simulation, you get a benefit by running a lot of simulations in parallel. I mean, you can run them in series, but it just takes a lot longer. And at some point, it becomes a bottleneck in your development flow, right? If you want to be able to, for example, run your CI/CD and say every check-in gets run, you run 100 different system tests. That can be very time consuming. You don't want your developers, basically stuck waiting for something that's going to take hours to run. So by using our batch APIs and simulations in parallel, you can speed that up dramatically. They can get an answer in minutes. So yeah, that's, and we've had very good response to that. As I mentioned, like Milvus Robotics, it's definitely sped up their development flow. It's a big advantage over running on a single system on your own desktop.
Maybe Mr. Kuta, if I understood correctly, what you presented was mostly being non-cloud. It was local systems, embedded systems. Have you any request to moving something like this into the cloud, to having embedded and cloud mixed somehow?
I would say that there's definitely, we've not engaged with a lot of customers on WebOS Robotics yet. So, but it seems, of course, obviously over-the-air updates to be handled by the cloud and sort of fleet management tasks. But we're primarily focused on the software that would run on the actual device. But it does seem, if you can solve the latency issues with having the controlling program be in the cloud as opposed to something closer on a local network, then it would also be useful.
Okay. Roblo, so the DRAG&BOT system is also cloud-based, as we have seen. So what about your customers? Do you have also requests for doing it locally, or are they fine with this cloud-based?
So the industrial customers always want everything locally. So for production and for in the factory. So a lot of times there is no internet. So when you deal with production itself, at the end you need everything locally. And but the cloud is a very good entry point. So for the initial settings or simulation and so. And so it's like a mix. So there are some clients that they use first the simulation to get into the product, and then they move to the local version, which is for us, so a good marketing tool.
Okay, so just out of curiosity, how many online users do you have actually in the simulation?
So currently we have more than 400.
Okay, that's quite
not at the same time. This is good because at the end, so the cloud needs some computer power and.
Mr. Hansen, so we have seen this multi-robot simulation, and I find it interesting. So, how many robots does the multi-robot simulation scale up to in a typical setting?
Well, with this current architecture I showed, it's a single level hierarchy ROS bridge. So it depends on like how fast you need your robots to get updates from each other, because I mean, it is being bridged together. We, feel comfortable with it running in the 4 to 8 robot range, but we're also looking at ways that in the future we can expand that to larger and larger numbers of robots. I do want to mention one other thing too. With 4 to 8 robots, you can get quite a bit of testing done as far as like, being able to do dynamic collision avoidance and collaboration and things like that. So we feel that, it is a pretty sweet spot right now, but we're also looking to expand that in the future. And we're open to, if there's people that want to work with us on that, and we're open to, having some discussion and working backwards from their needs.
Okay. Thank you very much also for that answer. Unfortunately, it's already 5:15 here, so we are at the end of our allotted time. So I would like to thank all of you once more for the quite interesting presentations, the demonstration, and also for participation in this rather short discussion round. I wish you all a fine day, and with that, I would like to close the session. Thanks again for having me here.